Hello, in this video, which is the 7th in a little mini series that I'm calling Basic Limit Theorems, we're going to start delving into the law of large numbers. And there's two different types of law of large numbers, which is called the strong law and the weak law of large numbers. So the strong law says that if we have some a random variable xj and their IID, and they have a finite mean mu, then the sample mean converges almost surely to mu, which is the population mean. Okay. Should be noted also that the converse is true, that if x bar converges almost surely to some finite constant called mu, then the population mean is also finite and equal to mu. Now we're going to omit this specific proof, but for the weak law of large numbers, we're going to prove it three different ways. And the weak law of large numbers is in a similar setting. We have a random variable xj and their IID, and they have a finite mean mu. Then the sample mean converges in probability to mu. Now we're going to prove this three different ways, which I think is kind of fascinating. So the first one, we're going to use the characteristic functions. So here's a note though. In video 2, in this little mini series, we showed that the convergence and distribution to a constant implies convergence in probability to that constant. Okay, so normally it's the other way around. Convergence and probability always implies convergence and distribution, but it's not the other way. Convergence and distribution usually does not imply convergence and probability. But if the distribution converges to a constant, then that 100% implies that the random variables converge in probability to that constant. Okay, and we prove that in video 2 in this little mini series. So now also that the Levy's continuity theorem says that if the characteristic functions of our random variable, x bar or whatever, converges to a distribution of another characteristic function, then that implies that the distribution functions converge. Okay, so now note that let's assume we have a probably, it's x is a constant, say mu, with probability 1, so it's the only data point. Then what's the characteristic function of this x right here? Well, by definition, it's the expected value of e to the itx. Then this says take each value here, plug it in for this x, and multiply it by its probability of happening. Well, there's only one value, so you plug in mu times probability of happening, which is 1. So this is the characteristic function of a constant. Okay, so we're going to remember that. So now let's look at our characteristic functions. We're going to show that this converges to some constant, which then implies that the distribution functions converge to a constant. And if they converge in distribution to a constant, then it implies convergence in probability to a constant. Okay, so the characteristic function of x bar is, and you can rewrite x bar as a sum of the x over n. And then I have a video called characteristic functions that show you this property that you can take that constant and put it in here, this arguments part right here. And then because these are IID, it's really, you can just look at one of them and then raise it to the nth power, however many you have here. Okay, so now we have this. Now let's look at a Taylor expansion of just this characteristic function here. And I'm just going to write down the results in our previous video, number 6 in this little mini series called the central limit theorem. I go into much more detail about looking at a Taylor expansion of our characteristic function about 0. But here we can just note that this is you plug in, it's a 1 t to the n I mu, and then plus little o of t to the n. That says that this is the remainder of our Taylor expansion, but that these start going getting to be so small when n gets large that we can essentially ignore them. Okay. So, but the little o notation can be rewritten as this. So you could like take a tn out and put a 1. That really goes to 0 fast. And so now if we can divide out a tn to both of those to get this situation, and then I write it like this because this is how my mind thinks about that this converges to the e, you know. So you have it n, and then you have a raised to the n, and whatever's here is in the exponent of e. So you have a t, this piece goes to 0, and then you have an I mu, which is this. Well, this is a characteristic function of a constant. So we just showed that the distribution, or the characteristic function of x bar converges to a known characteristic function of a constant. So that says that our distribution of x converges to a constant. C converges to mu, right there. So since x n converges in distribution to a constant, that implies that x n converges in probability to that same constant, mu. And so we're done. So that's the proof. That's the first proof that we're going to look at. So the second proof, we're going to assume that we have a finite variance of our x's. Same, you know, the data still has a mean mu, and the variance of x bar would be sigma squared over n. So thus, this probability, now if we can show that this goes to 0, that shows that xn converges in probability to mu. So by Markov's inequality, this is less than the variance of xn over epsilon squared. Well, the variance of x bar is sigma squared over n. And if you look at this and let n go to infinity, this does go to 0, which says that this goes to 0. And so xn converges in probability to mu. Now the third proof, we're going to drop the assumption of the finite variance sigma squared. And this is it's kind of a cool proof. It delves into what's called truncation of a random variable. But unfortunately, the proof is a little bit long, so we're going to dedicate a whole video to that proof, and that's going to be the next video, the 8th video in this little series. But before that, let's do a little example. Okay, so let's let xj from 1 to n be IID with distribution function f. Then the sample distribution function is defined as this. So fn of x is the number of data points less than or equal to this little x, which is that, divided by n. And this is for all x in the real number line. Okay, so that's how it's defined. So note that fn, you know, our sample distribution function, is a random variable itself for each x. We don't know what that's going to be until we plug in our x and we calculate it. Okay, so let's define another variable called yj. It's an indicator variable, and it's going to correspond to each data point, xj. And so if xj is less than or equal to little x, then it's a 1, otherwise it's 0. And the reason that we're defining it this way is that you can define the sample distribution function in terms of these y's. So remember, we want to know how many x's are less than that little x. And so if we add up the indicator functions for each data point, so the data point is either below the x or not. And if it's below, it's a 1. So this tells us the sum of these yj's, how many data points is less than little x. And if we divide it by n, then we get our sample distribution functions. So note that the yj's are independent because the xj's are independent. Okay, so these yj's are IID. Okay, and specifically they're Bernoulli with some p. You know, so that, you know, we're only looking at one data point. All right. Well, how do we calculate p? P is the probability of success, which is a 1, which is what this says. But to be a 1, it's the probability that xj is less than x. Well, that is how we define the population CDF. So the yj's are Bernoulli 1, and P, and where P is the population CDF. So now let's look at the expected value of the sum of these YJs, which we're starting to get into this piece right here. Okay, so the sum of Bernoulli's is binomial. So in the expected value of a binomial is NP, so it's N times cap F, or the population CDF. The variance of a binomial is NPQ, which then becomes this. Now, and so for each X, and by the law of large numbers, our sample distribution function. Now remember that, so the sample distribution function can be thought of as like a sample mean. You know, it's the sum divided by n. So by the law of large numbers, our sample distribution function converges almost surely to the population CDF, and it also converges in probability to the population CDF. Okay, so this is really important, especially in non-parametric statistics. This becomes pretty important. And then one final note is that the Glavinko-Cantelli theorem says that these convergences is uniformly in X. Okay, well, that's all I have for today. Hopefully you enjoyed it. If you did, please like it, subscribe so you don't miss the next one. And as a reminder, in the next video, we're going to prove the weak law of large numbers, where we drop the assumption of finite variance. So I will talk with you then. Thanks. Bye.